Okay, looking at some problems here now. Given a situation where we've got a graph which shows the number of wineries in the Hunter Valley from 1950 to 2000, and we want to describe how the number of wineries has changed over this period, including the rate of change. So we're starting at a particular point, and then it keeps rising. So obviously the curve's rising, and you notice it's starting to get steeper. So if we look at our graph, we can say our first derivative must be positive. And also, because it's concave up, our second derivative must be positive. So that's why we can make those two statements. Because the curve's rising, it's increasing. So first derivative must be positive because it's increasing. And the second derivative is positive because it's concave up. So these ones, what we can draw to a conclusion there would be the wineries are increasing. And they're increasing and increasing at an increasing rate. So that's what that type of curve means. It's increasing, but at an increasing rate. So for the curve, the function of x, the first derivative of a is 0, and the second derivative of a is greater than 0. So stationary, but concave up, which means it must be something like that. It must be a minimum turning point, because it's concave up and stationary. So that's where we have a first derivative equal, where you have a maximum turning point, so minimum turning point. So, number of people with flu is increasing over time. Also, the rate of the people with catching the flu is increasing. What would that mean for our first derivative and second derivative? So, if the number of people is increasing, well, the first derivative must be equal to 0. And also, the rate of which people are catching the flu is increasing. Our second derivative would look way greater than 0. So, our curve would look something like that. So again, we've got no numbers. We don't have to be totally accurate. We just need to be able to draw a curve that would put in that in terms of those. And notice we dn dt, so our horizontal graph axis would be t, and n is our vertical axis. Population of birds in a certain area is increasing over time, but the rate of population is slowing. So describe the sign of that. Well, if it's increasing, then our first derivative must be less than 0. But the population growth is slowing, which means it's still increasing, but not increasing it's increasing at a decreasing rate. It means our second derivative would be less than 0, which means our curve would look something like that. You look, it's still increasing, but it's slowing up. The population growth is slowing. So the number of koalas is studied over time. The initial number is 2,500. During this period, dn dt is less than 0. What does this say about the number of koalas? So, well, if our first derivative is less than 0, our koalas are decreasing. Poor little koalas. But if its second derivative is greater than 0, that means it's starting off fast, but then it's slowing up. So it's concave because it's concave up. So our graph should look more like this. It should be touching the curve, and it should be touching the curve at 2,500. I neglected that in that diagram, because the initial number was 2,500, and initial number means that t is equal to 0. So our graph only starts here. It shouldn't go over this side, because that means we'd be having a negative time. So and n would be there, because dn dt. So it starts at 2,500, and it's decreasing, and it's the gradient concave up, so it's slowing up. So it should show some concavity there. Number of unemployed people is increasing, and the unemployment rate is also increasing. A du dt, a d squared u dt, positive or negative? Well, they're both going to be positive, because it's increasing, and it's at the rate of which it's changing is increasing as well. So there's got to be a curve that looks like that, and they're both going to be positive. Number of cases of flu increasing. However, there was a rapid increase at first, but now that rate seems to be slowing. Sketch a graph. Well, it's still increasing, but it's slowing up. We shouldn't really show it being stationary, but it should be concave down the whole way. So that's some practical problems that we deal with, putting words into graphs and what does it mean in terms of the first and second derivative, so we can describe it mathematically from the actual given problem and situation.